In this clip, we're going to accelerate you into some of the ideas behind carousels and roller coasters. Now, we've noticed before that if we have a force, and we apply a force, for example, to a car, it will cause that car to accelerate. So forces cause accelerations. But that also means the opposite, that if you have an acceleration, it's caused by a force. So if you're going to accelerate, something's got to be pushing on you or pulling on you. So just where and how that force is exerted on you determines what you feel when you accelerate. Now remember, your body has a natural mass to it. So it wants to stay wherever it's at. That's your inertia. So if you experience a force to accelerate, as might happen when you're in a car, the mass of your body, the inertia of your body, well, it just wants to stay put. So what happens when a car begins to accelerate is, while you're sitting there, so let's say this is your back that you're feeling, you'll feel the force from the car on your back. It'll push against your back, and then the back pushes against the bodily tissues and so forth that are inside, and it keeps pushing. It'll all push you forward, and what you feel that force from the car as is a feeling of acceleration. It's almost as if you were being forced backwards, even though what the reality is that you're being forced forwards. So feeling of acceleration is backward. Notice that feeling of acceleration is very akin, in fact it's virtually identical to the feeling you would get being pressed down by gravity. In fact, if you had that feeling of acceleration backwards, and it was calibrated so it was precisely 9.8 meters per second, you could not tell the difference between that acceleration backwards, whether it was due to the force from the car or whether it was due to the acceleration of gravity. Even the most sophisticated instrumentation simply cannot tell the difference between acceleration due to gravity and acceleration due to actual motion. Well, let's say they have super sophisticated, but it's well beyond ordinary means to be able to deduce what is going on. So feeling of acceleration, whether due to gravity or due to simple acceleration in a car, it's the same sort of feeling. In fact, look here. If you have your regular weight, okay, that's going to give you a feeling of acceleration downwards, right, due to your weight. And we know W is equal to M times G. Now, you're also, if you start pressing on the acceleration pedal and you start accelerating, you'll have a feeling of acceleration backwards. Between this down feeling and the backwards feeling, they combine to give you an apparent weight that's sort of diagonal like this. And actually, the more you accelerate, the more that diagonal kind of stretches backwards, you see, as the acceleration gets bigger. So the two of them give you an apparent weight that's something very different than the actual gravitational weight. In fact, can you imagine that, let's say you were in outer space and you wanted to have something that was mimicking gravity? Couldn't you do just some kind of acceleration that could mimic gravity so that people could live more normally in conditions of weightlessness or ostensive weightlessness? You can, of course, and we'll show you how. First, let's take a look at a carousel, because that'll give us sort of the simplest idea of how we can do this. Notice how these people are flying out as this rotates around. Now, one thing that's important to remember is, you know that if this fellow right here wasn't tethered to the big stanchion here, If he wasn't tethered, what would happen is he would not go around in a circle like this, but instead he would go like that. He'd go straight off, and that would probably not be a healthy thing. So people would want to go in a straight direction, right? So, and that we remember that unless we provide some sort of acceleration, people either remain at the same velocity or they stop. And remember, the force provided by friction can provide that negative acceleration that slows people to a stop. And that's what fooled humankind for millennia into thinking there was some natural tendency for inertial materials to just want to stop. Actually, it just wants to keep doing whatever it's doing. If it's stopped, it wants to stay stopped. And if it's going and it has no friction to stop it, it'll just keep going at a constant velocity. But anyway, what I want to point out here is, in order for this to keep going, a person to keep going around in a loop, in a circle, that person has to have an acceleration to keep them in. There's essentially a force that's keeping that person rotating in a circle, a constant force, because if there wasn't a force, again, and now let's look at this rotation right here. If there wasn't a force going inwards, that person would just want to keep going at the same velocity and not kind of tilt at each point. So at each point along here, there's always a little force pushing that boy inwards. Now, interestingly, there's always the force that's going in, right? Force is pushing him in, but what that person is actually feeling is an acceleration, as if they wanted to keep going that way. So force is pulling him in, the feeling of acceleration, just as before here we saw here's the acceleration and the force, right, is pushing them forward. Feeling of acceleration is always in the opposite direction. So that's exactly what's happening here. Now it turns out that there's a super easy equation, and that is that acceleration that the person experiences to keep them going inwards, just enough to keep them going in a circle. That acceleration is just whatever the velocity is. You take that, square it, and then divide it by the radius, and that always gives you your acceleration. Now, if you want to, you can get a little fancier and say it's the angular speed times the radius, but we won't really mess with that too much. For our purposes, we'll just say how fast is this person going around, that's their velocity. Take the velocity and square it, divide it by this radius, and that's the acceleration needed to keep them going into a circle. So let's try to work out a few little examples. Let's say our velocity was 1 meter per second and our radius was 1 meter. Okay, so now let's see what we've got. We'll plug this into the formula, plug that into the V, plug the R in right here, and it's going to be, okay, I'm just rewriting the formula. A is equal to 1 meters squared, and we're or 1 meter per second, and that's squared, divided by 1 meter, and that should be, 1 meter, that turns out to be 1 meter per second, because these 2 meters or one of the meters cancels right from here, but it's squared, so that leaves 1 meter per second. Oh, that's not too bad. Okay, now let's see what happens though when I change the velocity, and now I'm going to make the velocity be, velocity is going to be, okay, V is equal to 10 meters per second. Okay, so, and we're going to keep the radius at 1 meter. Okay, so now we're going to plug in just like we did before. We'll say A is equal to 10 meters per second squared divided by 1 meter. And that, okay, what's 10 times 10? Because we're squaring. It's 100. And when we cancel things out, it's meters per second squared. That's, whoa! That acceleration is really a lot stronger. So I like the way your textbook phrases this. He says, making a tight, high-speed turn involves lots of acceleration. So that's why you can see in this next little clip how these absolutely insane people have to do a lot of gunning and acceleration to get those cars up on the side of the slope. So what was going on just there? Let's see, we had cars going around in a circle. Now let's guess that we had the velocity of those cars. You know, I'm just going to guess that they were doing something like 50 miles per hour. And if we do the conversion, that turns out to be 22.4 meters per second. Okay, so let's guess that the radius of that was about 100 feet. So maybe 200 feet across. I'm just guessing. So that would mean in SI units that we've got around 30 meters. So then the acceleration, you know, if we're looking sideways and here's the body of one of those cars kind of sticking, you know, I should draw that a little bit better here. Okay, we've got the body of a car and it's got its wheels, you know, as it's going around like this, you know, inside this cage as it's going around. Okay, so that's our car. And what is our car experiencing? An acceleration inwards. This is what's keeping this car so that it's actually going around in the circle. So it's experiencing a constant acceleration, and that's going to be v squared over r, and that's going to be 22.4 meters per second squared over 30, something like that. So that means the acceleration, when you calculate all that out, is around 16.7 meters per second, pushing in. So it actually feels the feeling of acceleration that car experiences. So remember, the person in the car is going to feel the acceleration kind of going outwards, and it's actually going to be forced inwards to keep it going back, you know, around in that circle. That feeling of acceleration outwards is 16.7 meters per second. Remember, gravity is just on average 10 meters per second if you round it off a little. So that person feels an acceleration sort of out like this that's even stronger than gravity. And that's pushing the car, right, into this wall, and there's a lot of friction there, and that helps keep the car from falling down. So it's able to keep going around, even though I think those people are totally insane. Now, this relates to one of the problems in Chapter 3. This is problem 5. It says, engineers are trying to create artificial gravity in a ring-shaped space station by spinning it. So here's a sample. Hopefully you can see it here. It's just what someone has dreamed up as a prototype space station that would be able to revolve. And let's say that it had a diameter, or a radius of 100 meters. How quickly would the space station have to turn in order to give the astronauts apparent weights equal to their real weight on the Earth's surface? Well, the real weight on the Earth's surface has a gravitational pull, G, that's 10 meters per second, right? So what we want is that the velocity of this going around like here, the velocity with which this would be spinning would be such that we'll have, it'll experience, well, here, let me erase this, it will experience an acceleration, which is v squared over r, that would be precisely the same as gravity. So what we really want is that this acceleration right there is going to be 10 meters per second, and that's going to be, well, what velocity we need divided by, and they tell us what the radius is. It's 100 meters. Oh, all we have to do now is solve for v squared. So I'm going to multiply both sides by 100, and then that turns out to be 1,000 is equal to v squared. So that means we have to take the square root of both sides, and then the velocity, if you plug in your little handy-dandy calculator, here's our handy-dandy calculator, so we're going to plug in 1,000, take a square root, and it's 31.6. Okay, so v is equal to 31.6 meters per second. That's how fast this has got to rotate. So what I want to show you now is a visionary movie, 2001 by Stanley Kubrick, and that movie shows a space station revolving just like this in order to reveal, or in order to have the astronauts experiencing a feeling that's very much like that of regular gravity. Of course, in Kubrick's 2001, they also experienced something quite different as well, but that's not the focus here.
Hello, Hal, do you read me? Do you read me, Hal?
Affirmative, Dave. I read you.
Open the pod bay doors, Hal.
I'm sorry, Dave. I'm afraid I can't do that.
Now let's move on to another one of the problems. Problem 7 says, when you put water in a kitchen blender, it begins to travel in a 5 centimeter radius circle at a speed of 1 meters per second. Okay, so 5 centimeters is equal to 0.05 meters. Okay, so that's the radius. How quickly is the water accelerating? Oh, well, that's easy. They're telling us what the speed is. We've got to calculate A is equal to V squared over R. Oh, okay, let's just plug it all in. So we've got the velocity is 1 meter per second, square it, divided by the radius, which is 0.05 meters. And, okay, let's just figure that all out here. Take our calculator. Okay, clear it, and we've got 0.05, and we'll take the inverse, and it's 20. So all of this is equal to 20 meters per second per second. So that's the acceleration. That's how quickly that water's accelerating. So let's see what happens to someone who experiences a little bit of that accelerating water. And now that we're back, we've got problem 8. And they say, how hard must the sides of the blender push inward on 0.001 kilograms of spinning water? So, as we just saw, the water will come out of the blender if it's not pushed back in. So, how much must be the force that's pushing this back in? Force is equal to mass times acceleration. We've just calculated what that acceleration is. It's 20 meters per second squared. They've just given us what the kilograms, what the mass is right here. So the force that must be pushing in on that little bit of water has got to be equal to mass times acceleration, which is 0.001 times 20 meters per second per second. And so all of that is just 0.02, 0.02. And what are the units going to be? It's force. So it's got to be newtons. And so if you don't have that many newtons pushing in, as you just saw, you'll get spattered pretty good. Now what happens on a roller coaster? If you go around on a loop-the-loop and you have that feeling of acceleration outwards, in other words, you're being pushed inwards with a force that is exactly that of gravity, you'll have a feeling of acceleration outwards that's that of gravity. Well, guess what? Between that feeling of acceleration outwards and actual gravity pulling you down, the two can balance. So you can stay right poised right here, momentarily anyway, and feel virtually weightless on a roller coaster. What I'd like to do now is I'd like to turn this discussion over momentarily so that you can meet the author of our textbook. His name is Lou Bloomfield. I've met him. He's a wonderful man. He's at the University of Virginia, and so it's kind of nice just this once to see his explanation of how roller coasters work. In light of everything we've discussed, I think you'll have a good understanding of what he's explaining.
Hi, I'm Lou Bloomfield from the University of Virginia, and I'm going to talk to you today about how things work. And the object I'm going to start off with is the roller coaster. And in particular, I'm going to look at 3 questions about a roller coaster and see how they illustrate a lot of physics. The questions I have in mind are, what's coasting? What does that mean? Why is it called a roller coaster? So that's the first question. The second is, why do you feel pulled around wildly as though gravity is all misplaced as you ride a roller coaster? And lastly, and most importantly, why when you go around a loop-the-loop and you're upside down at the top of the loop-the-loop, why do you still feel pressed into your seat? You're upside down. What's going on? So, to understand that, let's start with a demonstration. And the demonstration I have in mind is the classic parlor trick of pulling a tablecloth out from underneath the place settings. Now, it's not really a trick at all. It's just physics in action. It's a particular feature of physics known as inertia, an observed behavior of our universe, our world in general, that an object left to itself, that is at rest, stays at rest. And as we'll see in a few minutes, that an object in motion that's left to itself, that's not bothered, continues in motion, in fact, in a straight line at a steady pace. Now, I'm going to claim that the story of the roller coaster rests on this physics concept known as inertia. So here's the illustration. Here are the place settings. And for the added degree of difficulty, of course, we have to have some wine in the glass. So there we go. And physics is an experimental science. You know, if it doesn't actually happen, we don't teach it. So here are the objects at rest, and the claim is if I don't bother them, they'll stay at rest. Well, you know, as I pull this tablecloth, it's a slick, limp silk tablecloth. It's still going to bother the plates a little bit with what you know as friction. And in order to minimize that effect and to illustrate this beautiful concept of inertia, I'm going to work very fast, so that although these objects will get pushed on a little bit and they won't be completely on their own, I can minimize their effect by sort of swamping them by going so fast. So here we go. I choke up a little bit to give myself some room to get my hands moving fast. Ready? Get set. Go. So there, an object at rest stays at rest. So we've seen an object at rest tends to remain at rest until you bother it. And I have one more illustration of that same phenomena. So some bananas, a knife. Well, if I have a banana in my hand here and I let go of it, if nothing is pushing on it or bothering it, inertia says it should stay still. Now you know if I let go of it, it's going to fall. So there's a problem. It is not all by itself. It's being pulled on by gravity. So it's a little hard for me to show you the inertia of an object at rest when it's free in space. But if I work quickly, you'll get to see it anyway. So I'm going to work so fast that gravity doesn't have time to really influence this banana much, and it will illustrate its own inertia. It'll stay in place because that's its nature. An object left to itself tends to remain at rest. If it starts at rest, it remains at rest. And I'm going to sneak a knife through it while it's waiting around, minding its own business, being inertial. Ready? Get set. 2 half bananas. Well, that's an object at rest, staying at rest. Doesn't look like a roller coaster yet. Let's start moving. Let's start coasting somewhere. What's coasting? Coasting is the other part of inertia. The inertia that says an object in motion tends to continue in motion. In fact, in a straight line at a steady pace. And again, gravity makes this a little tricky, so I'm going to work fast. So gravity's a bit player in my little story. So here's a banana. If I get it moving and let go of it, so it's all by itself, apart from gravity, it'll coast. Straight line, steady pace, all the way out of the room. But I'm going to make it have a problem en route. It's going to coast right into the knife. And it's going to go through the knife, not because I'm pushing on it, you hope, I certainly hope, but because it will have its own inertia carrying it forward. Not push, just coasting. Ready? 2 half bananas. Well, still doesn't look like a roller coaster yet, but we're getting there. I can do the same thing with this ball. I can make it head off, and if I go fast enough, it's going to follow its inertia, very little influence of gravity. It'll go pretty much straight and true, and it'll leave the room again. But I don't want to have that happen. Instead, I'm going to start pulling on it. I'm going to begin to influence it. So this now changes life. It's not going to be purely inertial. I'm going to start pulling on it. and I'm going to pull it to its side. As it heads to the right, I'm going to pull it away from us. And I'm going to pull it around and pull it and pull it and pull it. And look what happens. It goes in a circle. It's trying to go straight, follow its inertia, but I'm not letting it. I'm pulling it around in a circle with a string. And this is starting to look a little roller coastery, but what if I do the same thing vertically? Ooh, now it's really beginning to look like a roller coaster loop-the-loop. Except you don't go around in a circle pulled in by the center on a string. You're pushed in by the car. Well, to do that, let's start with the car and the track. Car and track go around the loop-the-loop. Ready? Sure enough, the car is trying to go straight. That's its inertial behavior. But I'm not letting it. I'm pushing it into a center. Me, the track. I'm pushing, always pushing the car into the center. And it's loose in my hand, but it goes over the loop-the-loop anyway. It's trying to go straight. Well, the final demonstration needs the glass of wine. So let me go get the glass of wine. So we have the cart, the roller coaster itself going around the loop-the-loop, but we haven't got you in it yet. So let's put you in it. Well, let me get the track again. So here's the track. Pizza platter. The car, the roller coaster is the glass. You're the wine. And we're going to take all of you around the loop-the-loop. So here we go. The whole problem is starting and stopping. Ready? Get set. So you're going around the loop-the-loop. You're pressed into your seat. The seat's pressed on the track. Life is good. Now we have to stop. Whew. Physics saved the day.